So welcome back. And the plans for this week are to go through the final model, which we are going to include in project number 1. And this is a slightly more realistic model. It's something which favors people who have a physics background. So I wanted to give you a kind of overarching view on it. So you, at the end, you see what has to be done, because we are going to end up at the end with a 2x2 matrix and a 4x4 matrix. And these matrices are going to be kind of lookalikes of the 1-qubit case and the 2-qubit case. But we need to do some small manipulations. And I also wanted to give you a kind of background for this specific Lipkin model, why it is so interesting, and why you will encounter this one in many textbooks in physics. And actually, some of the first applications of quantum computing simulations was done with the Lipkin model or similar models, which we normally call spin-spin models. So these are models typically where you can rewrite your Hamiltonian in terms of Pauli X, Y, and Z operators. And that is your Hamiltonian. Now, for the Lipkin model, there are some manipulations which need to be done. And I just wanted to set them up. And next week, we will essentially just dedicate the whole session to discussions of project number 1. So then we won't have any lecture because the deadline is getting pretty close. Also this week, we will also spend a little bit more time towards the end of the lecture on just discussing the project. Okay, so the model itself is something which you will find as on background literature, and you will find papers by Ryan LaRose and collaborators who actually implemented the Variational Quantum Eigensolver for studies of the Lipkin model. You will find codes here, but I've also added a set of codes. So if you go to the lecture notes for this week and you go into the same folder where you find the Jupyter notebook for this week, you will also find an example with the Lipkin model where I've done some further tests, but here I've been using Qiskit. In the code examples, which you find here, then we're actually using the standard Variational Quantum Eigensolver in the same way as we've been using it before. So one of the things I want to do now is actually to show you some of the basic inputs to this model so you get some better understanding of what it is doing. So let's just switch to the whiteboard immediately. Now, this is what we in physics call a 2-level model. And we have 2 energy levels. So suppose now that we have a given number of particles, n, and suppose we have 2 particles. Now, it's a 2-level model in the sense that we can accommodate a given number of particles in the following way. So we have one level here, which has an energy of minus epsilon divided by 2. And then there is a new slot here where we have an energy of plus epsilon half. And in each of these levels, we can actually place as many particles as we want. So the type of quantum numbers which we are getting is something which we can now classify with in different ways. So we are going to add something which we will call for spin, J, and this is going to be equal to minus a half. And this is normally often written like a spin down, or just an arrow pointing down. And then here we have a J, and we're going to put the number Z here to indicate that this is a projection along a specific axis. So this is plus 1/2. And we normally label that one with a spin off. Then along this line, which you see here, we can then place as many particles as we want. So we can have as many slots. And we will label these slots, if we now have 2 particles, we will label this with a number P. So this has number 1, and this is number 2. This P occurs here as well, 1 and 2. That means that a specific state, a single particle state, which we would label like psi like this, is now going to be a tensor product of the state P with the state which now encodes this quantum number JC. And we would typically normally write this as P of JC. So these are the quantum numbers. That means that you can accommodate particles with a half spin, like these ones, and electrons, protons, etc. They are half spin particles, and we call them fermions. And for fermions, there is a postulate about the system that the total wave function has to be antisymmetric under the exchange of two particles. That means if you change two particles, it changes sign. Now, as a consequence, when you break this down into such a single particle picture, the consequence is that you cannot have more than one particle in each slot. So if you now have two particles here, suppose now that we have filled in these two slots, this is a two-particle system. So particle 1 has P equal to 1, and particle 2 has P equal to 2, but they both have spin down, or minus 1/2. So that means that the total wave function, then the two-particle wave function, is then the tensor product in the non-interacting basis of these two states here. Then you can obviously kick one of the particles up. Remember also that these particles are indistinguishable and identical, which means that you don't know if particle 1 is here or if it is here. And this is normally something you would set up in the wave function. So you can then assume that there is an interaction which allows you to kick one up here, for instance, up there, or you can kick one up here. Now, the total spin, if you look at that one, so the total spin of the system, this is normally called a spin projection. So this is the quantum number of the system. We call that JC. That is going to be a sum, in this specific case, from I equal 1 up to 2 of the single JCI quantum numbers. And if you now have minus 1/2, you see now that when you look at this system, we can have the following situations here. So let me just do that and just set up these specific cases which we can have in addition to the first one. So I'm just setting up here P, 1 and 2, 1 and 2. Then we have the same states up here, but this is spin up and this is spin down, spin up, spin down. So what we could have now is that we have the first particle is here and the next one is here. Then we have a spin down and a spin up. So that means that JC, the total one, is equal to 0. Similarly, I could now have this situation here, and that would again give JC equal to 0. Now, the first case was the one which was pretty simple. So I could have this case here. That will give me JC again equal to 0. So then I would have this state here would be T1, 1, and this would then be set together with the spin 1/2 and minus 1/2. So 1, 1, because P, this is P for particle 1 and P for particle 2. And you see now that we could have this case here as well, if you do the combinatorics. And that would also give us a JC equal to 0, because we have a spin up and spin down. And then we have the final case, which is just these two guys here, which have a JC equal to +1, because then both are in the upper case. So this is just combinatorics. So when we are setting up the Hamiltonian matrix to diagonalize, we have in principle, we have 4 different states. But what you see now is that what you have is that you have a total J, C, which is either -1, 0, or 1. That means that there is an angular momentum which is equal to 1, because this JC is just equal to minus J plus 1. This goes all the way up to 0, and then we have 1 of J -1, and finally J here. And in this case, we have only 3 possible values. Now, what we're going to see is that the Hamiltonian commutes with these quantities, which means also that they then have common wave functions. So there's a lot of physics jargon here. Now, what we could think of now is that there is a part of the Hamiltonian which allows you to break a pair like we would do here. So suppose you have prepared your state in the initial state, and then there is something which acts on the system and promotes one up here. So you could think of these two guys being a pair, which is then broken. So in that case, we are just promoting one particle up, but then we could have a case where we are promoting both up, because this is a 2-particle interaction. Now, you can continue with this model here and look at a case where you have n equal to 4. So you can have 4 particles, you can have 5, you can have 3, as many as you want. So what happens then is that your lowest line state, without any interaction, when you now think of spin -0.5, so this is -0.5 here, and we put in these slots with P1, but now we need to augment it with 1, 2, 3, and 4. So we have 1, 2, 3, and 4. And then one possible organization could just be this one, which we now are going to fill in. So it's again, these states are the same in the 2 levels, but this is a spin-up case. So it looks like an inverted ladder. You could have a ladder where you walk 1, 2, 3, 4, and then all states are like that. But now we just have a ladder with 2 steps in terms of spin. So you could now think of filling in these slots here. And then you see that the total JC, which is the sum of all the spins, is equal to -2. Alternatively now, if we have an interaction which acts on 1 particle at a time or 2 particles at a time, we could now kick up 1 here. And then you see that we would have 1 with a half minus a half, 0, and then 2 with -0.5. That could give us a total J, which is simply equal to -1. So you can now start building new states of the system, which may look like, now I'm just gonna write this in a more schematic way here. So I'm just gonna put 1, 2, 3, and 4. So we could keep the particles here, but then we could promote this one up here. So this is left as a vacancy. And if we then count the spin values, we have -0.5, -0.5, -0.5. So that's -3.5 plus 1/2. So that simply gives us a JZ, which is equal to -1. Now, what we could have is another type of state where we have promoted 3 of the particles to the higher level, or we could have just 2 here and then 2 here. That's another possibility. So again, it's just the combinatorics. So in the previous case, you had, if you look at the combinatorics, which you can do then, you have now 2 slots here and 2 spins. So that's 4 possibilities by which you can place the particles. And that's going to give you 6 possible rearrangements. And then you can continue and do the combinatorics here, because now you have 8 slots in total, because you have spin up and spin down, and you have 4 particles. So in this specific case, this is going to be the total number of states you can make is now going to be total number of states is a combinatorial factor, which is given by 8 slots, which you have, 2 spin-ups and 4 for every spin value. So that's 8 possibilities which you can fill in. And then if I have 4 particles, this is the total number of arrangements I can make. So that means that what you would get then is simply, if we now just do the combinatorics here, it's just then 5, 6, 7, 8, and divided by 2, 3, and 4. So that takes that one, and this takes this one. So we're left with a 2 here. So this is equal to 70. the 70 possible ways by which we can reorganize these particles. If you go back to the previous case, in this situation, we had 4 slots and 2 particles. So that means that the total number of states then is equal, of 2 particle states, is now equal to 4 slots and 2 particles, which then is obviously equal to 2, 3, 4 divided by 1, 2 divided by 1, 2. So what we're left with then is just a factor of 2, which then cancels here, and that's equal to 6. And you can see that when you count them and you just do the reshuffling of them, you have 1 here, and then we have 6 more here. Now, in the case with 70 states, I'm not going to draw all 70 because that's pretty boring, but you see the basic pattern. So in principle, if you're not looking at specific symmetries, you would have a matrix, because these are the number of states, which would be a 70 by 70. However, these Hamiltonians, they do actually now commute with spins, which means that I can block reduce these dimensionalities 7 to 70 to smaller dimensionalities. And that gives an easier task to diagonalize. Now, one of the things which you would see here in this particular case is that you would have JC equal to 0. And then you can continue with many, many of these arrangements. And you could have the final situation where you have all up here. And that's a JC equal to +2. So for 4 particles, n equal to 4, then what we have is a set of values which go from for JC, which are given by -2, -1, 0, +1, and 2. So these are the possible values, which means that the total J, the total angular momentum, is equal to 2, because these degeneracies with degeneracy, and so we are going to get exactly the same energy. So we have a degeneracy which is 2 times J plus 1. So there's a lot of physics in here, and I know that not all of you have taken a course in quantum mechanics, but this is more to prepare a little bit the ground and for the way we're going to rewrite the Hamiltonian in terms of spin operator. And at the end, since this here gives us 5 spin values, if we are going to diagonalize in that basis, we will actually get a 5 by 5 matrix, instead of us diagonalizing by brute force a 70 by 70 matrix. And the reason for that is that we have many such states, which will essentially give the same energy, where we now have J equal to 0, J equal to -1, and J equal to +1. However, the states where you are here, or rather this one, this is unique. There's only one such state with J equal to -2, and there is only one with JC equal to +2, because we have filled in all the 4 slots in the highest lying level. So the 2 extreme values, -2 and +1, are just represented by one single state. However, for many of the other ones, as you can see, this JC equal to -1, I could now promote this particle up here, or I could take and promote this one up here, this one up there, etc., etc. So there are many more ways of just breaking away one of these and reaching the JC equal to -1. However, when we use this as a basis, this is a way to simplify the dimensionalities of the problem. And this is something which is used again and again in physics. And for us, it has a big benefit, because if we were to write the Hamiltonian in the standard way, which is normally given by second quantization, and I know that not everybody is familiar with that. So we would then have a Hamiltonian, which would have a one-body part, which looks like some constant epsilon half, the energies. And then we are summing over the JC values, and we sum over these values P, and then we have the JC value, and then it's common to use creation and annihilation operators. I'll just quickly say something about these. So this has a JC, and this has a JC here. And I know that not everybody's familiar with them. And this sum runs over, so let me just, this sum here runs over -1/2 to +1/2. So this operator here creates a particle. It fills into vacuum, plain emptiness, particles with quantum numbers P and JZ, and this one destroys it. This is going to give us the energy of the non-interacting piece. Then we are going to add an interaction piece, and this interaction piece is going to be given by a term which looks like this. So we are just summing over one value of JC, but we look at two values of P. So we create a state here. So this is JC dagger. This has an AP of JC dagger. And this has an AP prime. And then it has a minus JC. And this has an AP. And this has a minus JC. So plus minus JC. So what this one is doing, this term, so let me, by the way, write the final one. And this has a sum over JC of P prime. And then I have an AP of JC, an AP prime minus JC. And then it has an AP prime, and this has a JC, and this has an AP of a JC. Now, what this is doing, if I look at the first term, and I now pick a specific state, and suppose now that we have filled in particles here, so this is P equal 1, 2, 3, and 4. We have a spin down and a spin up, and P here, and P there. So if we now look at the first term, this term which goes like minus V divided by 2 here, of JZ of P prime, and then I have this creation operators of JC of AP prime of JC, and multiplied with an AP prime minus JC, and then an AP minus JC. So what we see now is that this operator here, what it is doing when I now look at these states is that I have a particle in the level E here, which is destroyed with it can have a minus spin. So this could be this one, which is here with P equal to 1 and with spin down. And then this is now being promoted up to the next state because it has a quantum number P here. So it stays in the same quantum number P. So that means that it gets promoted up here, one of them. So it has P equal to 1, but it changes spin. The next state, which I have, is a P prime, so it stays the same. So you could say now P equal to 1 in the equation here, but it changes sign for the spin. And then the next one could be this one, where I have a P prime equal to 2 here. And now this also changes spin from minus JC to plus JC. So this is an interaction which now picks up two particles from a state below or from a state above, because the minus then forces this to have the opposite spin value. So we can think of this as something which leaves a hole here, which we mark like this. It leaves two particles here, and it's often called a two-particle, two-hole excitation, because the interaction now boosts up two particles at a time. The other term, the W term, takes only one at a time. And that would be what we normally call a one-particle, one-hole excitation. So this is a lot of physics jargon. And for those of you who are familiar with this type of way of thinking, using what's normally called second quantization or the number representation, this is a way by which we typically interpret specific physics excitations. Now, the thing which is interesting for us is that this system, which we have, can be manipulated a little bit with the so-called spin operators. So this Hamiltonian, which you see written like this, can be rewritten in forms of the following operators. So we can rewrite, and I'm just going to make a long story short. And in the lecture, in the Jupyter notebook, you will find all the derivations, but this is not so important for us when it comes to the project. So what I wanted to focus on now is actually what we are going to calculate. Now, for this Lipkin model, you can actually systemize this in a very efficient way when you have a given number of particles and that specific Hamiltonian. But what we can do now is can rewrite in terms of spin operators, in terms of spin operators and Pauli matrices, of so-called spin operators and Pauli X, Y, and Z, and identity matrices. And this is what I wanted to show you now. So at the end, you get a Hamiltonian, which we can easily rewrite in the way we want to for a quantum computational calculation, as we had for the 1-qubit case and the 2-qubit case. So there is a kind of long way to go here, but the main thing which we can do then, so one is that this H0, which we had, can be written out in terms of an operator JC. So this is now an operator, where this is simply the sum of epsilon, and then it takes all the single particle states, the particles which we have, and it has this operator JC of I. And this is something which we will rewrite in terms of a Pauli matrix. So and I'm coming back to this. So this is going to be actually rewritten in terms of a Pauli C matrix. Actually a sum of Pauli C matrices. So let's wait a little bit for that. Then we can rewrite this other term, this H1 here, which we previously had in terms of this variation and annihilation operators. So this is going to be given by a J plus and a J minus operator. And this J plus and J minus, they are given by Jx plus minus an imaginary part and a Jy. And Jx is going to be interpreted in terms of a Pauli X matrix, and Jy is going to be interpreted in terms of a Pauli Y matrix. So but we are going to put up that a little bit later. And then we have the final term, which is this operator H2 here. So this H2, and let me just put up this correctly here so I don't... let me just rewrite it. So this is going to be given by 1/2 of W, and then it's going to contain an X of I, or J plus squared minus J minus squared, plus a normal ordered operator. These are all operators. And this JC here, this JC is something which we are going to rewrite in terms of 1/2, and then a sum over all the particles we have in terms of a Pauli C matrix. And the C of I is going to be equal to a term. So this should have a minus sign, and this also has a minus sign. And the C of I is just the Pauli X C matrix. These operators, J plus and J minus, can then be rewritten in terms of 1 over square root of 2 over sum from I equal 1 up to n. And then I have my Pauli x plus minus y I multiplied with the imaginary constant I. So that means that if I do that, so this is just a Pauli x matrix. This is just 0, 1, 1, 0. And this quantity here is just a Pauli y matrix, which is 1, minus 1, 1, and 0. And this has a minus I and a plus I. Okay, so when we do this now, I can actually rewrite my Hamiltonian in terms of these matrices. And we are going to see now how we can set these things up. So it's going to be an epsilon half. There's going to be a sum over I equal 1 up to n. And then I have a sum of Pauli x C matrices minus V half. And there's going to be a double sum, I less than j. You will also find all these derivations in the Jupyter notebook of xj minus yi of yj. And then I have in addition a minus w half. And there is a double sum, I less than j, and xi xj plus yi of yj. So if I take the case with two particles only, for j for n equal 2, then what my Hamiltonian is going to look like is going to be equal to an epsilon half, and there's going to be a z tensor product with I plus a y tensor product with z, because we have two particles here. So if we are thinking of this as two qubits, but you will see that we are going to simplify this further. So we're going to make it a little bit simpler. But in principle, it's going to be, if I now put this w equal to 0 for simplicity. So in the project, we can actually easily run with that. And that's going to have a Pauli x times a Pauli x minus a Pauli y tensor product with a Pauli y matrix. And then we would have a similar one if we add this W0 term. Now, there's something more here, which is a little bit important, and that is the Hamiltonian, which we are going to get when we now look at two particles only. And we are going to calculate some specific expectation values. So if you look at the Hamiltonian here, we have written that in terms of these operators. So when I act on a specific state, I should also remind you that JZ has a commutation rule for angular momentum, which is equal to plus minus J plus minus. We have a new commutation rule, which J plus and J minus, which is equal to 2 times JC. Then I have the famous one, J squared with JC. So they have the same eigenstates. And we will also find for this specific problem that these are equal to 0. And we have H, this is the Hamiltonian of JZ, is also equal to 0. So it means that the eigenfunctions, eigenstates of H, they are also eigenstates of the angular momentum squared, where this angular momentum squared, J squared, is just equal to JX squared plus JY squared plus JC squared. And again, this are rewritten in terms of Pauli X and Pauli Y and Pauli Z matrices. This again means that if I act with JC on a state which has angular momentum J and projection JC, this has a specific quantum number and the same eigenstate. So this is now an operator. I put a hat on it. And without the hat, this is just the eigenstate, the eigenvalue. So this is an eigenvalue problem. If I act with a number operator, which in principle is just the sum over all the states which I have, I equal 1 up to n of AI here. If I act on that one, on the same state of JC here, I get the number of particles, which is, in this specific case, since we have spin half objects, it's 2 times JC multiplied with J and JC. Then in physics, there is something which we can use to set up the whole set of matrix elements. So there's a J plus operator. When that acts on J, I'm just reminding you of these quantities, because this is something which will allow me to set up the full Hamiltonian matrix. So I would have a J over J plus 1 minus a JC of JC plus 1. And this is multiplied with a J of JC plus 1. So I increase with J plus 1. And this is called a ladder operator. So in this case, I add plus 1 to JC. And then I have a similar one for J minus, acting on a state with JC. And this allows me now to construct the full Hamiltonian matrix. So for those of you who have taken a course in physics and quantum mechanics, you've probably seen these things before. So this is a JC minus 1. And this is multiplied with a J of JC minus 1. So we step down 1 unit value for JZ. So if I now look at the case again with n equal to 2 here and J equal to 1, which means that they have a degeneracy, which is given by minus 1, 0, and 1, then what we will see when we are setting up the Hamiltonian matrix, the full Hamiltonian matrix, we will now need to look at the different states, because this is going to give us a J equal to 1 and a JC equal to minus 1, which we identified as this specific state. 1, 2, spin down, spin up, right? That's that specific state. Then if I then look at other possibilities here, so the other possibility is obviously, so this is only one possible state, and I have J equal 1 and JC equal to plus 1. And the only possibility I have here is this one, spin up and spin down. And then I have 4 possibilities where I break a pair. So the J equal to 1 and JC equal to 0 has 4 possibilities. So what I can do now, since my Hamiltonian contains these 3 possible states, I need to look at either plus minus. So this is J and JC, and I'm going to use a shorthand. So I have the operator JC and 1 plus minus 1. So if I now look back at the eigenvalues which I get, I should then get, for this specific case, just plus minus 1. Then I can continue because my Hamiltonian contains these operators. If I now go to the next case, I need to calculate 1 plus minus 1, and then I have a J plus minus squared, which appears in my Hamiltonian, and then it goes to 1 plus minus 1. And if I do the algebra correctly, this should give me 2. Similarly, I have 1, 0, and then I have a J plus or minus. This is the operator which can connect me to that. So these are operators. We're going to put hats on top of them. And in that case, I would have a 1, 0, for instance, because that brings me back. And if I do the math here, I should get 2. If I take this number operator, that when it acts with 1 and 0, it gives me 2 again. So when I put all these terms together and I look at my Hamiltonian matrix, I will get a matrix to diagonalize, which is going to look like minus epsilon, 0. I have this term V. I have V here, 0, epsilon, 0, W, and 0. Now, if I look at the states which I'm connecting, this state, so let's just rewrite it before we take a small break here. So we have now, for the two-particle case, epsilon 0 and V, 0, W, 0, V, 0, and epsilon. Now, if we look at the states we have been connecting now, so this is spin 1 and minus 1, this is spin 1 and 0, and this is spin 1 and plus 1. And here again, I have the matrix element of 1, minus 1, which then links with the Hamiltonian and the state 1, 1, 1, 0, and 1 plus 1. And this is again linked with the expressions which we are setting up here and here, and also this expression here. These are the expressions which we need when we are setting up the Hamiltonian matrix. And this one will be 1, 0, and 1, 1. Now we are going to make a simplification now in project number 1. And for most of you, if you're interested, so this would look like something which cannot be simplified to a 1-qubit case. But if we now say that W is equal to 0, so let's use that as the case we're going to work through in project number 1. If W is 0, it means that we cannot connect 1, 0, 0 with 1, 0, 0 here. So that's going to be 0. And we can take out this column here. This means that the only states we are interested in are actually these states, because you see now 1 minus 1 to 0 is 0, 1, 1 to 0 is 0. So we can then, if we do that, then this matrix which we have simply collapses into minus epsilon, V, V of epsilon. And this is something which we can then rewrite as a 1-qubit problem. So coming back to the project, this means that here, this matrix which we have, we can rewrite that in terms of a poly Z matrix plus V times a poly X. So for project 1, it's okay if we just put W0, because that makes life simpler. Now, if we were to look at a case like the full case here, we would have to introduce 2 qubits, because we could think of that as a reduced 4x4 matrix. And that would complicate life. So my suggestion is that we just put W0, and then we run the calculations like that. There are ways by which we can simplify this case, actually. If you now look at what we have, and this is interesting. So if you take a closer look here, there is nothing which says that you should organize your states this specific way. You agree on that? So we could simply now interchange columns and rows of the matrix. So I could decide now that these two guys change. And then I would do the same here. If I do that, then I can actually reduce this problem to 2 small matrices. So and we could keep W. So if you now look at the case with 1, 0 and 1, 0, that links only with itself. Whereas the 1, 1 does not link to 1, 0, so they already decouple. So take a look at this matrix. So this was a simplification, but we don't need to do that simplification. So if we now reshuffle, so I just interchange this row with that one. No, sorry, these columns. And then when I've done that, I interchange this row with that row. So if I do that, then my matrix would actually look like this. So I would have a minus epsilon, I would have V, And I would have V here, and then I would have epsilon, 0, 0, 0, 0, and W. And now I've simply interchanged because there is nobody who tells me that I should keep that order which I had before. So this will be 1, 0. And this is obviously 1, 0 here. And then I have a 1, 1. And then I have 1, minus 1. That means, again, that I can just look at this block like that. And then I simply can read off this eigenvalue here if I had W. So there will be 3 eigenvalues. This eigenvalue here is just straightforward. It's just given by W. So that's going to be the same all the time. And the only thing I need to diagonalize is just this case here. And this is the only one which then will depend on the interaction type which I have. So we are going to use the same trick when we now move into the 4-particle case, which is going to give us a 5 by 5 matrix. But then we can simplify it to 2 blocks, one which is 3 by 3 and one which is a 2 by 2 block. So the way we've set up the Hamiltonian here is going to help us a lot. So when I solve this sub-block here, this is something I would simply calculate with these 2 Pauli matrices, as we did the 1-qubit case. And then when we come to the 4-particle case, we are going to get a 3 by 3 matrix and a 2 by 2 matrix. The 2 by 2 matrix is something which we will solve exactly like we did here. But the 3 by 3 matrix is something we have to rewrite a little bit. So this is what you need to implement, starting from a Hamiltonian, which in the beginning looks a little bit intimidating. So if we go back to the Jupyter notebook, before we take a break here, if you look at the Jupyter notebook, what I've done is, and don't be intimidated by all this stuff here, is actually something which I have included for the sake of completeness for the physics aficionados. Because this is what a typical physicist would see, the way you would rephrase this in terms of second quantization. And then you can introduce these operators, which are called quasi-spin operators, and you can actually rewrite the whole Hamiltonian in terms of these operators. And what you will see here is just me demonstrating that these quantities obey the commutation relations for angular momentum, these specific choices which you see here. And when you go through all these boring exercises, this is not very exciting. This is simply to show that these commutation relations are obeyed. And when you scroll down, you can rewrite the Hamiltonian in the way which I put up here. This is the way you would rewrite it in terms of these operators. And then if you move down, you have the final expression here in terms of these operators. And you can then show that the Hamiltonian commutes with J squared, so they have the same wave functions, and the same with the JC and the number operator. And when you've done that, you can then start constructing the Hamiltonian matrix, and you use these operators because you have one state which is explicitly defined when all the particles are in the lowest level or in the highest level, and then you can construct the other ones. And when you do that, all these exercises, this is the Hamiltonian matrix you end up with. And this Hamiltonian matrix, as you can see here, there are empty spots, and we are going to rewrite this one as a 3 by 3 block and a 2 by 2 block after the break. So this is just a long story made very short, but I wanted you to see the background so that you see that this is not something which comes out of the blue. This is the way a standard physics Hamiltonian would be written in second quantization in this specific way, which you see here. And then you have to transform these operators into Pauli X, Y, and C matrices. And this is a cumbersome thing. So we have a more complicated Hamiltonian than this one. We are going to have something which is called the Jordan-Wigner transformation, which then transforms these operators one by one. And that can give us a long string of Pauli operators, which makes life more complicated. So the Lipkin model belongs to this class of models where we, at the end, can write the Hamiltonian in terms of Pauli X and Y and C matrices with some transformations. So this is a kind of overarching view on it. And you can, if you're interested, you can go through this, but we just give this as a kind of background information for you all. So welcome back. The symmetries which we now saw through this Hamiltonian for the two-particle case is something which we will see popping up again in the four-particle case. Now, keep also in mind that what we have done here for the two-particle case, instead of having a 6x6 matrix, which we would have to diagonalize, we have actually reduced it by using these quasi-spin operators into a 3x3 matrix. Let's now look at the four-particle case. So you saw also that we could rewrite the matrix by simply reorganizing the matrix elements, because there's nobody who forces us to keep a specific ordering of the states. So if we then rewrite it, we see now that these symmetries pop up in a very nice way, that we get a submatrix here, which does not link with this one, because these are all zeros, which you have here. So that means that we can solve this part separately, and then we solve this part separately. And that's actually us now simply taking this 2x2 matrix and rewriting it in exactly the same way as we wrote the one qubit case for the simpler Hamiltonian. Then what we could do now is to look at the four-particle case. So for four particles, we have a maximum value of the angular momentum, which is 2. And this has a degeneracy, which now gives us the following values: -2, -1, 0, 1, and 2. So these are, in principle, this is going to lead to a 5x5 matrix, because I have 5 possible spin values. And the way, instead of a 70x70 matrix, which would be the case we would set up in a brute force manner. If we use this basis, we would need to calculate specific matrix elements. So we would have a JZ, which then connects. So this is a JZ operator. When it's a hatted, it's an operator. It has total angular momentum J equal to 2 and projection plus minus 2. This is simply equal to plus minus 2, because it's the value of JZ, which in that case is either +2 or -2. Then I have a similar set of matrix elements. If I have a 2 or ±1, and then I have my JZ acting on 2 ±1. So we need all these combinations when we are setting up the final Hamiltonian matrix. So this is either ±1. Then we have this lowering or raising operators, this J plus and J minus. I'm just setting up all the possibilities here, and I'm hoping I'm writing them off correctly. So in this case, I would have a J plus or J minus squared. And this can then link a state with 2 minus plus 1. And this takes a value 6. We have 2, 0, and then I have a J plus minus squared, and then 2, and this goes to minus and plus 2. And that gives us 2 times square root of 6. And then I have my 2 plus 2. And then I have my J plus minus, and that lowers us down. We still have the value of 2 here, but then it goes down with steps of 1. So we gives us 0, because I have J plus squared. So that is J plus acting on the state, and then J plus acting again on the new state. So the first time it acts, J plus, it gives us from +2, gives us +1, and then I act again on it, and it brings us down to 0. So this will then link a matrix elements in the Hamiltonian where we have a Jz equal 2 or -2 to a Jz equal to 0 element. And if I just plug in the values, I will get 2 times square root of 6 here. And then we can continue with all the possibilities which we have to 0. And then I have these operators J plus, J minus. And then I have a J minus, J plus, which then appears in the W0 term. And this also links because this lowers and then raises. So it goes from 0 to 0. And that gives us, if I do the algebra correctly, it should give 6. And then I'm just setting up the 2 final ones where I have 2 plus minus 1. And then I have a J plus minus, J plus minus here, and a J minus plus. And that should give us a 2 plus minus. So that gives also 6. And then finally, I have my 2 plus minus 1 of J minus plus and J plus minus with 2 and plus minus here, and that gives us 4. So the states which we have would then be given by 2, 2. So this is the value of J, and this is the value of Jz. And then we have 2 plus 1. We have 2, 0. And then we have 2 minus 1. And finally, we have 2 minus 2. So that means that the states which I'm going to use to set up the Hamiltonian matrix will be a set of 5 states. So my matrix is going to be a 5 by 5 matrix. So what I can do then is then to use this specific order. So I'm going to use this order which just follows in a slavish manner from the lowest to the highest. So I start with 2 minus 2. I do 2, no, so minus 2, 2 minus 1, 2, 0. And then I have 2 plus 1. And then I have 2 plus 2 here. And then here I would have 2 minus 2. There's only one of these possibilities. 2 minus 1, 2, 0, and 2, 1. And finally 2, 2 here. So if I then plug in these values, I get minus 2 times this constant epsilon. I get 6, and then I have 6 square root times v. So it comes from one of those matrix elements, and then I have 0, 0. Now, and then I have 0, and then on the diagonal, I have minus epsilon plus 3w. There's a 0, there's a 3v, there's a 0. I have a 6v here. There is a 0, there is a 4w, there is a 0 here, and there is a square root of 6 times v. There's a 0, there's a 3v of 0, and then I have an epsilon plus 3w, and then I have a 0, and then there is a 2 epsilon here, there is a 0, there is a 6 square root of v, and 0 and 0. Now you see again that there are many zeros here. So we are going to reorder rows and columns as we did before, because this order which you have here is something you can change. I mean, you don't need to have that explicit order, right? So if you then reorder it, you're going to see now that if I interchange this row with that row, and then I do a new one, and then interchange rows again, I can actually rewrite this Hamiltonian matrix as follows. So I can rewrite it, but now I interchange, and then I get a minus 2 epsilon square root of 6v, 0, and then I have 0, 0. So I'm going to get a 3 by 3 block, So this is going to be 0, 0, 0, 0. And then I'm going to have down here minus epsilon plus 3w. I'm going to have a free v. It's going to be a free v and epsilon plus 3w. So that's going to be the final one here. And here I'm going to have 0, 0, 0, 0. And then I will have square root of 6 times v. And then I have a 4w. And then there is a square root of 6 times v. There is a square root of 6 times v here. I have a 0 here. And you see the matrix is symmetric. So this is just a simple reshuffling of rows and columns. And that means that what I've done now is actually to set up states. So in here, I have 2 minus 2. Here I have 2, 0. And here I have 2, 2. And then I have 2 minus 1. And I have 2 plus 1 here. And then the same down here. I then have 2 minus 1. And then I have 2 plus 1 here. And 2, 2, 2, 0. And finally 2 minus 2 here. So you're fully allowed to, because I mean the order is something you decide. And you see now that due to all the zeros, things simplify. And at the end, we have now two submatrices, which we need to look at. And this one is something which we already have. So if we take this one, the red one, then we know that we can rewrite this one as a minus epsilon plus 3w and 3v and 3v and epsilon plus 3w. And this is something which I can rewrite as a 3 times w of I minus an epsilon times a Pauli Z matrix plus 3 times v times a Pauli X matrix. And this is again the exercise which we had for the simple 1-qubit case. So this is the smallest block is something which we can translate immediately into a 1-qubit problem. So that means that when we do the measurements here on the full Hamiltonian, we can actually use these simplifications to actually set up this in terms of a problem here, which has a 1-qubit case. And now we're going to take the next case and see that we can rewrite that one as a 2-qubit case by simply adding a row with zeros. And the way we're going to do that is as follows. So what we do in this case is now to say that I identify my state 2 minus 2 with 0, 0, qubit 0 and qubit 0. So this is nothing but 0 times 0. So just a way to label state. And then I'm going to identify my 2, 0 with just 0, 1. I could have done 1, 0 if you want to. And then I have my 2, 2, which I identify with 1, 1. So that means that my matrix is actually going to look like, so if we take that submatrix, and if we call these by different names, so let me just call this one for H double prime, and this is going to be H prime. Then my H double prime is something which I can rewrite as the following matrix. And I would have a minus 2 times epsilon. I have my 6 square root times v, 0, but now I'm adding an additional one because I have the 0, 1 state, which I have not included. And then I have my, so this would be my 0, 0. This is my 0, 1. And then there is the 1, 0. And then I have the 1, 1 here. Then this would then be 6 times v. And then I have 4w. I have 0. and then I have square root of 6 times v, and then comes the zeros. And finally, I have 0, square root of 6 times v of 0, and finally, I have my 2 epsilon here. And this is something which I now can rewrite in terms of poly Y, poly X, and poly Z matrices. And then I have my Hamiltonian, which I then can set up for making measurements. So if I then do the algebra here, and I look at some of these parts, so if you, because now it's instructive to look at, suppose now we just take this part and that part. That's something which we can rewrite in terms of a poly Z matrix, because this is something which you then can set up as a sum of different matrices. So you could have one along the diagonals, which is pretty easy to set up, because that could be identity matrices and poly Z matrices. And then if you look at the non-diagonal ones, so if we just take that example, so let's just look at that one. So I could take this matrix times 6, and then 6 times v, and then 0, and then the rest are just zeros. This is a matrix which I can simply rewrite as I have a 6 times v, just this constant, and this is then multiplied with I1. This is an identity matrix, so this is I1, which would be the upper block here, times poly X 2 matrix. And now I'm just going to set up what this means here. So let me just put it up here properly. Times x2 here. So this x2 is nothing but a 1 poly multiplied with a poly X matrix. And poly X is just 0, 1, 1, 0. So that matrix is something which I could put up like this. And then I have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, and then all zeros here. And if I do the algebra, I can actually write this out. So this x2, which I have here, is just defined as this specific matrix here, where I have done the tensor product. So this is actually the tensor product of 1, 1, 0, 0, and then tensor product with 0, 1, 1, 0. So these are just ways to rewrite the matrix. And if I look at this one, this can then be rewritten in terms of a set of matrices, which looks like 6 times v, and then I have this I1 multiplied with x2, and then I have an I1, I2 plus a, and this is something I can rewrite in terms of a poly matrix, and this is an I2 here. So these matrices here, like a Z1, that is the same as poly Z tensor product with identity matrix. I'm going to set up these terms here. So when you see these definitions, this is just defined as these tensor products of x2 here. This is just an identity matrix tensor product with x. When you see an I1, this is just simply an I 2 by 2 tensor product, another I 2 by 2. So that means that it's simply just 1, 1, 1, 1 here, and zeros. So these are pretty simple matrices which are being set up here. So this is a kind of notation. When I put this in, this is 1, 2, and x 1, 1, and 1, 2, etc., etc. Then, if we now look at these other matrix, so if we take this 0, 0, 0, 0, and then we have a 0, 0, and then a square root of 6 times V, 0, 0, 0, 0, 0, and then I have a square root of 6 of V, 0, 0. And what I'm doing then is simply that I'm taking this part here, this one and that one, and just writing it out as a matrix by itself. And this is something which I can rewrite in terms of the following. And you will see that this is nothing but a 6 times V, and this will contain a Pauli X matrix. So this is multiplied with, so that's the Pauli X with a tensor product of the identity matrix, the 2 by 2 identity matrix, minus the Pauli Z matrix divided by 2 here. So if I add everything up, what I'm going to get is that my Hamiltonian is going to be equal to this W, and then I'm going to have these matrices. I'm going to have an I1, I2, so these are matrix multiplications, minus W, and I take this C1 times C2, and the definitions are given by these quantities you see here. And then I have a plus a W minus epsilon of the C1 minus omega plus this epsilon of Z2, which then has to be translated into the basis I want to perform the measurements. And then I have plus square root of 6 times V divided by 2 here. And then I have my X2 plus X1 plus Z1. So when you don't see the tensor product, these are matrix multiplications minus X1 and C2. Now for the project, you can easily set W equal to 0. So for P1, project 1, feel free to set W equal to 0. For N equal 2 and N equal to 4. Now, as a challenge, if you want to, you could look at the case where you have more than, more than 4 particles. If you want to have that as a challenge, then your matrix is just going to grow larger. But in essence, this is what you will end up doing for the Lipkin model. So that means that what you would have is a matrix, which you can then reduce to a 5 by 5 instead of a 70 by 70 by using these quasi-spin operators. This can be rewritten in terms of 2 blocks, which don't talk to each other. One, due to the specific symmetries of the Hamiltonians, which only links together these states. And then another block, which only links together these states. So there are some deeper symmetries with the Lipkin model, which will allow you to set up this in a general way for more than 4 particles. And you can do this for 5, 6, etc., etc. So there's nothing which hinders you in going for greater systems. However, when you translate this into a quantum computing algorithm, what you would end up with then would be you having to set up a problem like this one, and then a similar problem like this one. So in our case, it breaks down. Instead of having an artificial 3-qubit block, which will be an 8 by 8 matrix with 3 rows which are 0 and 3 columns which are 0, we've broken this down into one qubit case and 1 2-qubit case. And this is essentially the problem which we have at the very end of project number 1. So if you have the 1 qubit case functioning and the 2 qubit case functioning, if that is giving you the correct eigenvalues with the VQE, then you should be able to, in principle, to implement the Lipkin model as well. Now, one of the things which we have not discussed and which we are not expecting in project number 1 is to go beyond the ground state of the system. The variational ansatz which we have chosen is an ansatz where we typically go for the ground state of the system. Now, if you go back to one of the codes which we have here, I just wanted to bring up something which is relevant for the project, but which is not something you need to think of. Nope, nope. Okay. So let's just look at that one, and let's look at the code which we have here. So one of the things you can do is if you want to test things with Qiskit, this is possible, but you should, when you write your own code, you should actually have everything written out in terms of the Pauli X, Y, and Z matrices. But the example which you find here is an example where we now use Qiskit and the compute the minimum eigenvalue. And in this specific case, we actually partitioning the matrix. So I wanted to show you this one so you can see how you can implement what I put in the lecture notes here on the whiteboard. So if you now look at the simple matrix here, this is just your Pauli J equal to 1 matrix. And in that specific case, it just returns a Pauli X and a Pauli Z matrix like this. If you then look at the J2 decomposition, you then have the two matrices which you set up. So in the original numbering, these states were 1, 3, and 5. So these are the terms which I just put up here. And these are the terms which you then would have to translate into your own gates here. So for the smaller block, then you already have a simple expression for it. So you have a Pauli X, Pauli Z, and an identity matrix. But then for the other one, you would actually need to set up these specific expressions which we described. So this is just to show you how you can actually set it up if you want to, as a small hint. Now, one thing you can do is also to set up the states in the initial guess. Like the way we've been setting it up is not the most efficient way. And this is something which you could explore in project 2 if you want to have more sophisticated ansatses for the initial state. So we are just going to look at rotation of the qubits which we have. But one thing which we could actually look at then is a slightly more sophisticated, because the simplest one, the simplest ansatz which we can make. So let's just go back to the Jupyter notebook here. No, the whiteboard, sorry. So the simplest possible ansatz, which we also discussed in connection with a 1 qubit case, is to start with something which runs like this. Ansatz for the 2 qubit case. This could then be given in terms of a set of rotational matrices. So we write now this simply as a qubit 0, and then qubit 1. So these are the initial states. And it's pretty common to have these as 0 and 0. That's pretty common. And then what we did was to put up these rotation matrices. So you could think of having an Rx and an Ry here. And you would do the same thing here. An Rx and an Ry. Now, this will often not give a very efficient way for the variational calculation. So typically what you would add in addition here for the 2 qubit case, for the 1 qubit case, this is actually straightforward, because then you would simply just have the system as it stands here. Now, for the 2 qubit case, what you typically would add them in order to entangle them, because that will often give you a broader set of ansatzes for the ground state and also for the excited states, is actually to add a C0 gate or a CX gate if you want to, or CZ gate. So you could now have a C0 gate, and you would write it like this, and then you would have entangled the states, because in this particular case, the two states are not entangled. but you have made a linear superposition for the first qubit and for the second qubit. But what happens here is that you could now get something which could be qubit 0 and qubit 1. And let's say this is proportional to 0, 0. So this is the first one is qubit 0, now the other is qubit 1, plus, let's say, 1, 1, plus the transformed angles, multiplied with some coefficient alpha. This gives often a better ansatz. So this could then be the kind of state which you then would prepare. And with that preparation, you're then ready to make the measurements. So for the one qubit case, it's pretty simple because your measurement would be simply you adding a Pauli Z gate, or Pauli X gate, or whatever, and then perform the measurement in the basis of that one qubit case. But for the two qubit case, it can actually be useful to look first at the case where you don't entangle, where you don't have a C gate, and a case where you do entangle. So we don't know before you've run the calculation whether this is a better choice or not. This is something which we can also discuss in more detail for project number 2. So there is an alternative for project 2 for those who want to continue with this quantum computing approach. And there is a method which is called an adaptive variational quantum eigensolver, which is an improvement to the variational quantum eigensolver, which we've been looking at now. And then we could also explore different ansatzes. You can take the Lipkin model and extend this to more than 4 particles, etc. So there is a variant in project number 2, which then explores further this variational quantum eigensolver and simulations of quantum mechanical systems. So that's a possibility for those who are interested. So I'm going to stop here because this is essentially what I wanted to say about the Lipkin model. And next week, we are going to look in more detail into the project itself. So we will just have a working session where we discuss the project. That's the kind of basic idea for the next lecture. So that means that we don't have a lecture next time.